Good morning, dear students. In the last period, we have studied about the extensive and intensive properties, the properties that depends upon the mass and size. If it depends, then we call it as a extensive property. But if it does not depend upon the matter or the mass and size, then we call it as a intensive property. So this volume is an extensive property, whereas the temperature or density are the intensive property. We have even seen it by showing you the uh, particular type of figure that if we have a box or you can say a cuboid, and then we have the temperature. Initial temperature was V, initial volume was V, and temperature is T. If we separate it by using some partition. So when this is separated by using some partition, my dear students, so if we divide it into these two smaller parts, then the volume becomes V by 2 and the temperature remains same. The Yes, this is how if we divide it, then the volume turns out to be V by 2 in each case, but the temperature still remains the same. And as the temperature remains the same, we can say that temperature does not depend upon the size and matter that is present into the system, but volume depends upon the size and matter present into the system. And that is why volume is an extensive property, whereas temperature is an intensive property. Now, my dear students, today we want to study about the um, enthalpy change of a reaction, or we want to study about the reaction enthalpy. So today we'll study the thermochemistry part of thermodynamics. That is what I can say, that today we should study about the thermochemistry, where the various heat exchanges during the chemical reactions we are going to study about. First, we should study about the enthalpy change of a reaction. That is what it is known as the reaction enthalpy, delta RH. In a chemical reaction, my dear students, reactants are converted to products, and it is represented by the form of the chemical reaction that we write reactants that gives us the products. The enthalpy change accompanying a reaction is called reaction enthalpy. This is the definition of the reaction enthalpy. The enthalpy change accompanying a reaction is called the reaction enthalpy, which is denoted by delta RH. If we want to write the formula for delta RH, that is the sum of the enthalpies of products minus sum of the enthalpies of reactants. Again, in a better mathematical form, if we want to write it, we can write it as is equal to sum. For explaining the sum, we put the sign sigma ai hi products. So first we write the sum of the enthalpies of products, and then we write the sum of the enthalpies of reactants, that is sigma I BiH reactants. Here, my dear students, the sign sigma is used for the summation. AI represents the stoichiometric coefficients of the products in the balanced chemical equation, and BI represents the stoichiometric coefficients of reactants in a balanced chemical equations. So AI and BI are the stoichiometric coefficients. AI stands for the stoichiometric coefficients of the products, and BI stands for the stoichiometric coefficients of the reactants. Now let us understand it with the example. For example, if you look at this, we find that for the reaction CH4 plus 2O2, that gives CO2 plus 2H2O. This is the reaction for the combustion of methane gas, which produces carbon dioxide gas and water. The enthalpy of the reaction is the sum of the enthalpies of the products minus sum of the enthalpies of the reactants. That is the molar enthalpy. Here this M represents the molar enthalpy, that is the enthalpy change when 1 mole of substance is either produced or reacted. So HM is the molar enthalpy of CO2 when it is in the gaseous state, molar enthalpy of H2O when it is in the liquid state. But as it is 2 moles have been produced, we need to multiply the molar enthalpy with 2. And then the molar enthalpy of methane gas, that is what? And the 2 times the molar enthalpy of oxygen. So you can see that molar enthalpy of oxygen in the gas, and as the 2 moles have been produced, we multiply it with the 2. So while calculating the enthalpies, we just multiply them we just multiply the molar enthalpy with their stoichiometric coefficients also. And first we write the sum of the enthalpies of the products. This is what are the enthalpies of the products, and we subtract the enthalpies of the reactants. So this is how we can calculate the enthalpy for any particular reaction, my dear students. Let us understand it. Here, my dear students, we write HM, which is the molar enthalpies of any substance. Now, suppose if we have the reaction A plus B plus A plus B plus energy, that gives C plus D. Such reaction, in this reaction, energy is required or energy is absorbed. So when the energy comes, A and B react with each other and gives us C and D. Without this energy, the reaction is not going to be happen. So above is the endothermic reaction, and reactants gets energy to make products. So these reactants get energy, and that is why the products are formed. So we add some energy to the reactants, and as the energy is being added to the reactants, the products are formed, and that is why the energy of product is more than the energy of reactants, because when energy is added to the reactants, the products are formed. So products will have the higher energy than the energy of the reactants. So this such reaction, we call it as an endothermic reaction. And for any such endothermic reaction where energy is being added to the reactants and then products are formed, we can say that the energy of products are more than the energy of reactants. So if we represent them into if we plot the graph for the energy versus the reaction coordinates, on y-axis if we represent the energies, then we can see that the energy of the reactant is less than the energy of the products, and products are settled at higher energy level as compared to the reactants. So this is what we can say about the endothermic reaction, and this is how we truly understand the endothermic reaction. The reaction is done, but the reactions that we do it in the laboratories or we do it in the open system, they have the constant pressures that we have seen, my dear students. So in when it comes to the constant pressure, enthalpy of product is greater than the enthalpy of reactants. So delta AI, but when we actually want to calculate the enthalpies, we do the reaction at constant pressure or in the laboratory. So enthalpy of product is in that case enthalpy of reactants. That therefore delta AI HI product is greater than the delta BiH reactance, and that is why delta RH is going to be positive, my dear students. And for the endothermic reactions, we can say that the enthalpy of the reaction has got the positive values, because the value of delta AiHI product is more than the value of delta BiHI reactants. So you can see that from the graph itself that the energy of the product is more than the energy of the reactants. The energy of product is more than the energy of the reactants, and that is why the enthalpy of product minus enthalpy of reactant gives us the positive value, and that is why we can say that in endothermic reactions delta H value is going to be positive. So it is written over here that enthalpy of reaction for endothermic reaction is always positive, and delta RH is positive for the endothermic reactions. Now let us study about the exothermic reactions. So when you have the reactions like A plus B that gives C plus D plus energy, here in this reaction you can see that energy released or energy is produced during this reaction. Such reactions, the above reaction is called the exothermic reactions. So those reactions in which energy is produced or energy is released, we call them the exothermic reactions. Now here what happens, there is certain energy present with the reactants, and then when the energies, when the products are formed, some energy is released, and that is why the products have lower energy than the energy of the reactants. So here we can say that energy of the reactant is more than the energy of the products. That means enthalpy of the reactants is also going to be enthalpy of the products. But we are all aware that delta H is equal to enthalpy of products minus enthalpy of reactants. So this value, which is negative or which is having negative sign before it, is more than the value of this. So ultimately we are going to get the negative answer. I hope you understand. So when we have the reaction where the reactants combine with each other and they give us the product and some energy is produced, such reactions are known as the exothermic reactions. In the exothermic reactions, what happens? The energy of the reactants is more than the energy of the products, and as the energy of the reactants is more than the energy of the products, for exothermic reactions, what happens? Enthalpy of the product is less than the enthalpy of the reactants, and that is why sigma AiH product is less than the sigma BiH reactants. And finally, delta RH is going to get the value less than 0, and if any value which is less than 0, we call it negative value. So enthalpy of reaction for the exothermic reaction has negative value or less than 0 value. That is what we can easily understand from these examples or from these graphs or from these ideas. So we can summarize as, my dear students, that if we have the reactions like A plus B plus energy that gives C plus D, such reaction we call it as a endothermic reaction. And for endothermic reactions, the value of delta H is always going to be positive. Same way, if we have the reactions like A plus B that gives C plus D plus energy, such reactions are called the exothermic reactions. And for exothermic reactions, the value of delta H is going to be negative. So if energy is needed, delta H will have positive value. If energy is released, delta H will have the negative value. Remember, delta H is nothing but the change during the or change in the enthalpy during the change. Now, what are the applications of the enthalpy of reactions? So, knowledge of enthalpy change is required when one need to plan the heating or cooling required to maintain an industrial chemical reactions at constant temperature. So, if we want to maintain the temperature during the chemical reaction in the industry, whether it is required to be heated or whether it is required to be cooled during the industrial process, that has to be determined by knowing whether the reaction is producing energy or whether the reaction is releasing energy. If the reaction releases energy, we need to cool it. If the reaction requires energy, then we'll have to heat it. So this is how, my dear students, we understand about the industrial conditions. Second, enthalpy of reaction is also required when we want to write or calculate temperature dependence of the equilibrium constant. So when we want to determine the temperature dependence, how an equilibrium constant depends upon the temperature, we should have the knowledge of the reaction, whether it is endothermic or exothermic. Now the next uh, thing we want to study about is the standard enthalpy of reactions. We have studied the enthalpy of the reactions. Now we want to study about the standard enthalpy of reactions. Enthalpy of reaction depends on the conditions under which a reaction is carried out. So, how much energy, whether it will be produced or whether it will be required, that depends how or at what case or in what condition the reaction has taken place. It is therefore necessary that we must specify some standard conditions. So we need to specify some standard conditions for this. The standard enthalpy of reaction is the enthalpy change for a reaction when all, remember these things, when all participating substances, may it be reactants or it may be products, both. So here the meaning of all participating substance means they may be reactants, they may be products. So all the participating reactants and products are in their standard states. So the first thing is the reactants and products must be in the standard state when we want to determine the standard enthalpy of the reactions. So we want to study about the standard enthalpy of the reactions, and for that we need to know that, or we have to make sure that all the reactants and products are present in the standard state. Now what is the standard state? That even we need to understand. So standard state of the substance at specific temperature is its pure form at 1 bar. So when we have 1 bar pressure, what is the physical state, or what is the uh, pure form of that substance at a given temperature? For example, at more than 100 degrees centigrade temperature, for 1 bar pressure, water is going to be gas. Between 0 to 100 degrees centigrade temperature, for 1 bar pressure, water is going to be liquid. So this is how we understand about the standard state of the substance. Let us look to understand few examples to understand the standard state. Standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. Standard state of solid iron at 500 Kelvin is pure iron at 1 bar. So usually we take data for the standard state at 298 Kelvin and determine, or we usually use 298 Kelvin temperature to determine the standard state. But this is usual case. We can have some other cases even. So standard conditions are denoted by adding the superscript, bar and circle to this symbol. So now if we want to write the standard enthalpy of the reaction, we will write delta H and bar. So delta RH bar, that is the standard enthalpy of the reactions. So this is how the standard enthalpy of the reactions is denoted, by putting bar on it as a superscript. Now we want to study the next term, that is the enthalpy change during the phase transformation. We know that, my dear students, that solid turns into liquids and liquids turns into gases and solid sometimes sublimates. So these are what they are known as the phase transformation, and here we want to study about the phase transformation in our class. Phase transformation also involves the energy change. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, that is the atmospheric pressure, and during the phase change, the temperature generally remains constant. So let's have a look at this. We were talking about the ice, and when the ice melts during the phase transformation, the temperature remains the constant. So that is the 273 Kelvin or 0 degree centigrade. So during the phase transformation, the temperature remains constant. Water solid form, that is your ice, gets heat and it turns into the water. Now at this time, this is what it is, the process which is known as the fusion of ice or melting of ice, and we have the enthalpy change found for this reaction per mole. For 1 mole of water or for 1 mole of ice that is converted into 1 mole of water, 6 kilojoule energy is being utilized. Here definitely it will be used. So it is an endothermic reaction and the sign is positive. So delta fusion or delta H fusion in standard condition is 6 kilojoule per mole. Here delta fusion H is the standard enthalpy of fusion of ice. Now my dear students, if water freezes, so what happens? H2O liquid, which is 1 mole, it releases the heat and it turns into the ice, that is your 1 mole ice. During this, the heat is released, so the same kind of reaction is written, it is inverted, and that is why the sign actually changes. And during this process, that is what we call it delta freeze H standard. So for the freezing, the same amount of energy per mole is released rather than the energy is being absorbed. And this is what it is known as the standard enthalpy of freezing for water. The enthalpy change that accompanies melting 1 mole of solid. Now we are going to study the definition. The enthalpy change that accompanies the 1 mole of solid substance in the standard state is called the standard enthalpy of fusion or molar enthalpy of fusion, that is denoted by delta fuse H bar. So this is how we understand the definition of enthalpy of fusion. Once again, the enthalpy change that accompanies melting of 1 mole of solid substance in standard state is called the standard enthalpy of fusion or molar enthalpy of fusion, which is denoted by the delta fusion H. Melting of solids is endothermic reaction, so all enthalpies of fusion are positive. Water's, Water requires heat for evaporation. So you can see that this water H2O liquid, when we heat it, it turns into the water gas, that is your vapor or steam. At constant temperature of its boiling point, TB, and at constant pressure. So if the boiling point of water is TB, then at TB temperature, water turns into the steam. And here the process which is known as the vaporization. And for this, for per mole of water, for 1 mole of water, when it turns into 1 mole of steam, total energy needed is 40.79 kilojoule per mole. So this is how for the transformation of water liquid into the water gas, we need 40.79 kilojoule per mole energy, or for 1 mole of water to be converted into 1 mole of steam, 40.79 kilojoule energy is needed. So delta vaporization at standard is the standard enthalpy of vaporization. If we want to write the definition of standard enthalpy of vaporization, we should write it as the amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure, that is 1 bar, is called its standard enthalpy of vaporization, or it is also called the molar enthalpy of vaporization. Once again, the definition of standard enthalpy of vaporization or molar enthalpy of vaporization: amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure, that is 1 bar, is called the standard enthalpy of vaporization or molar enthalpy of vaporization. Now, my dear students, we want to study about the phase transformation, which is known as the sublimation. The sublimation is the direct conversion of a solid into its vapor. So that is what it is known as the sublimation without passing through the liquid state. We know that solid carbon dioxide, which is also known as dry ice, sublimes at 195 Kelvin with delta sublimation energy is 25.2 kilojoule per mole. Same way, my dear students, the naphthalene sublimes slowly, and for this, for 1 mole of naphthalene, we need the sublimation energy, that is 73 kilojoule per mole energy is needed as a sublimation energy. So if you want to determine the definition, standard enthalpy of sublimation, that is delta sublimation standard, is the change in the enthalpy when 1 mole of solid substance sublimes at constant temperature and under the standard pressure, that is 1 bar. So this is how, my dear students, we understand the enthalpy of sublimation. The magnitude of enthalpy change depends on the intermolecular interaction in the substance undergoing the phase transformation. For example, now we should know that the magnitude of enthalpy change depend upon the intermolecular forces of attraction in the substance that is present. So let us study it with the example. The stronger hydrogen bonds between water molecule hold them tightly in the liquid phase. So this hydrogen bond makes them to stay in the liquid state, and these hydrogen bonds hold them tightly. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker, and thus it requires a less heat to vaporize. So 1 mole of acetone as compared to the 1 mole of water, if we compare them, this 1 mole of acetone can be easily vaporized as compared to the 1 mole of water. So this is how, my dear students, we understand the various enthalpy changes. In today's class, my dear students, we have studied about the various important terms that are related to the enthalpy changes. We have started studying about the enthalpy of the reactions, which is known as the reaction enthalpy. That is, the enthalpy change accompanying a reaction is called the reaction enthalpy. We should calculate it by using the formula delta EIH products minus delta BIH reactants. We have seen that for the endothermic reactions, EP, that is the energy of product, is greater than the energy of reactants, or we can say that enthalpy of product is more than the enthalpy of reactants, and that is why for endothermic reaction, the value of reaction or value of delta H is always greater than 0, which is a positive value. But if we think about the exothermic reactions, energy is released, and that is why the energy of a reactant is less is uh, greater than the energy of products, and that is why the enthalpy of product is less than the enthalpy of reactants, and that is why while we calculate the delta RH, or while we calculate the reaction of enthalpy of reaction, we have the enthalpy of reaction less than 0 or negative value. So for, we can easily summarize that for an endothermic reactions, delta H will have the positive value, but for an exothermic reactions, the delta H will always have the negative value. If we look at the applications, we should know that if we know the enthalpy of reactions, we can easily understand that during the chemical process, if energy is released, we need to cool to maintain the temperature same or to maintain the constant temperature. But if heat is released, then during the chemical process we need to heat it to maintain the constant temperature. Same way, my dear students, when we want to determine the dependence of the equilibrium constant on temperature, we should know whether the reaction is endothermic or exothermic. Then, my dear students, we wanted to study about the standard enthalpy of reactions. So, standard enthalpy of reaction, the first condition is that all the reactants and products must be there in standard state. Standard state is the state of a substance at 1 bar pressure when the specific temperature is given. We have studied the various examples that how we determine the standard state of iron and the standard state of methanol. We have studied about the enthalpy changes during the phase transformation. So enthalpy change accompanies the phase transformation. Either it is the enthalpy of fusion or it is the enthalpy of uh, uh, freezing. We have seen that fusion and freezing are the uh, opposite kind of reaction. So when we invert the reaction, the value remains the same, but just the sign has been changed. So enthalpy of fusion for 1 mole of water is 6 kilojoule per mole, but enthalpy of freezing for 1 mole of water is minus 6 kilojoule per mole. We have studied about the enthalpy of vaporization. For vaporization, the enthalpy of vaporization is plus 40.79 kilojoule per mole. From these values, we can easily understand that in liquid state, the value is very high because the hydrogen bonding present into the liquid keeps it or hold the water molecules very tightly. We can even, or we have even understood about the enthalpy of sublimation when 1 mole of ice is directly converted into the um, 1 mole of dry ice is directly converted into the gas. We have studied that for dry ice carbon dioxide, the enthalpy of sublimation is 25.2 kilojoule per mole. For naphthalene, the same enthalpy of sublimation is 73.0 kilojoule per mole. This is how, my dear students, we understand the various types of enthalpies and various reactions. You must have noted that when we reverse the reactions, the value of enthalpy has the sign changed, and if initially it was positive sign, that turns to the negative sign, and if it is initial negative sign, that turns to the positive sign. My dear students, I hope, my dear students, you have enjoyed the class. Happy learning.